Okay, I think we've got everybody here that wanted to be on time. So welcome to the last lecture of this supercomputing course. And what we're going to do today, so this is the wrap-up lecture, is we're going to look at the assignment again. I'll give you one answer for how it could be done. And then I've looked at your submissions on the website, and so I've looked at some of the more common mistakes and pitfalls, and so I'll go over those and share them with everybody so that you don't have to make them again. And then once we've done that, and during that, you can ask questions in the chat, and we can discuss it at more length if you want. That's okay. We have time today. But then towards the end, I will go over to a few general best practices in doing supercomputing or scientific computing that are just good to know, and that will save you trouble in the long run. So a bit of lecture towards the end on some good practices. By the way, most of you or a lot of you have submitted to the website. Not every assignment was complete. Don't worry about that. As long as it shows that you worked on the material and you ran something through the scheduler, that's really all we ask for. I want to have you play with the material, and it's okay to make mistakes. In our usual summer school, you would make the mistakes, raise your hand, and we'd explain you what went wrong, and you would correct it there. And we just don't have the chance to do that exactly here. We've tried obviously with the hands-on yesterday, and I'm hoping that is helpful, but that's okay. If you haven't submitted anything yet, the Dropbox on the website will be open until the end of the day, so you can still submit then. It does mean that you have the answer, but I already said it actually doesn't matter so much that you have the right answer or not, but that you worked with it and that you ran it. So that being said, a lot of you got the answer perfectly fine. You got GNU Parallel to do its job and submitted it to the scheduler, and it ran. So congratulations. So what was this assignment again? What were we doing? So we had this script that executes almost 100 repeats of a computation of a bond breaking time. And this was the potential that this bond was feeling on the right here. And all 96 repeats of this computation, which just have different random numbers and are otherwise the same, but they could be run in parallel. And so you are supposed to see how long the script takes. And I ran it during the first lecture, so it was something of the order of 14 minutes, and then use GNU Parallel to create a modified version that runs these tasks in parallel, but in a way that sort of does automated load balancing like GNU Parallel can do. Submit to the scheduler and then see how long it would take. So that was our task, and obviously we're going to try and see how much use we can get out of these 16 cores of a single node of a teach cluster. By the way, I just noticed that I forgot to say what the course code is. The course code today for the attendance is 1. So take the test and enter 1. Okay, so one answer. Well, the left answer is just a serial. The left part is just a serial task that we had. I stripped out a few comments just so that everything would fit on the slide, and we can see the difference between the serial and the parallel one. So this was the serial version where everything runs one at a time. We have our for loop here. We had our Python module that we had to load. We had some variables. We used those variables to call bond break and to time it. And then at the end was this magic awk line that selects all of the detected breakages. People are saying that the answer is incorrect. That's weird. Don't try again then. I'll double check in a second if I made a mistake there. The answer for the parallel scripts is on the right here. And so one thing we had to do is we have to load the GNU parallel module so that we have the parallel command. The parallel command is here. And then we have to give it all of the cases in some sort of form. And so there's a few ways you can do that, but you want to basically have a list of S values running from 1 to n reps. And so it turns out that just doing curly brace 1 ... $n reps did not work. That is unfortunate, but that's because it doesn't know what n reps is when it tries to figure out what this range is and leaves it alone. So the way around that is to actually have bash print this expression, which will say 1 ... and then the number in it. So this will, and then evaluate that expression to actually get the range. And then this syntax dollar with parentheses actually takes the output of a command and stores it into a variable. So range now is just a string of 1 space 2 space 3 space 4, etc. until 69. An equivalent way to do that is to say range equals $sec n reps, $n reps. Sec is an external command, so it's not when we're leaving bash and running another command, but it's fairly standard on Linux machines to have this. And so that's another way to get essentially the same. What we would just want is this list of S numbers in the range, and then we call parallel. So with parallel here, I've chosen to take the approach where you give it a template. So the template command is bond break, and then the first parameter, the second parameter, the third parameter, and then here's where the seed was supposed to go. This was where $S was. That becomes these curly braces. And then we want the output names. And in this case, rather than assigning them to variables, I just put them in as they are. As I said, this is one answer. There are slightly more elegant ones, but this will work. And it will substitute, GNU parallel will substitute the curly braces. So it's bash's job to substitute the $ ones. It is GNU parallel's job to substitute the curly braces. By the way, this line is too long to fit on one line on the slide. These slashes at the end are continuation characters. So if this is in a bash script, the last character on the line, it basically glues the two lines together as if there was no new line. That's all that means. And that's a kind of convenient way to express long commands. And then at the end, I have to have a set of values to substitute for. And so that's the triple dollars and dollar range. Okay, and then the awk line is the same. So this will do in parallel these cases. It will substitute them and generate the commands. Another thing that I've used here is the -j job log option. So what that does is, in the simplest case, just prints out each of these commands when they are run into a file, and then also keeps track of how long they take, and whether they were successful, whether they exited with no errors given, and some other properties. And so that actually sort of can be used to take the place of both the echo repetition here and the time command, because I could look at this file and see which cases are done already and how long they took. So it's kind of a different format of the output, but the same information is there because I'm using this job log option. Now, if you run this, and if you have run this, then you would have probably seen that this takes about 1 minute and 22 seconds, or it fluctuates a little bit because data has to be written to the file system, and so there's some jitter there. But something of the order of a 10 times speed up is what we get here. So this 10 times speed up is not 16 times, which is the number of tasks we have. And that's precisely because of the unused cores that are inherent in a load imbalanced situation. You could try, I don't really recommend it, but you could try and do a manual breakup of these in sets of 16 and run 16 at a time, and then the next of 16 to see the effect that we had in the first lecture, where we saw that it was much more efficient to do it with GNU Parallel. But what this means, it's about 16, it's 10 over 16 is the efficiency, so that's about 60%. And if you've used the SEFF command, the SEF command, and then the job ID, it will tell you an efficiency, and you would see that in this case it says about 90 something percent, and here it does say 60%. So it's just that there were no more jobs to do, but there were still some cores busy with their jobs. That is what we're seeing. You could even try and play, if you want to see how this works, do more repetitions, and you'll get a better speed up just by pure chance, right? The fraction of wasted computation is rough, or the amount of wasted computation is roughly the same. It's just whatever's trailing, but the size of it will be bigger, and so you'll get a better. The more you have to do, the better your efficiency will be. Let me just take a second to look up the code for this course. Okay, so about the course code, if you haven't tried Trace yet, then you can have another chance. It seems like it did like your answer of 1. 1 is the correct answer, but then it multiplied that answer by 0 at some point, and then it got 0, and that was a failure. So classic bug. Try again. The course attendance code should be 1, and it should be working now because I just unchecked that. Okay, so this is one way to do it. There are other ways to do it. If you don't want to get into this trouble with having the number of repetitions in a variable, it's true. If you just said range is 1.96, then that would have worked. The trouble now is that the next time, if I want to change that, I have to look up every possible occurrence of 96. And so it's usually better to keep things stored in variables for sort of future use. Okay, so the overall timing is a question. Where do you get that from? You can do 2 things, but the overall timing here I got from Ceph. And you could also add extra commands in here. The job log, I don't think shows the overall one, but it shows how much each of them took. But I could check and see. Yeah, no, it just gives it per job. So you could put a time command in front of the whole parallel as well. So it's rather than doing it in front of bond break, and then you just get 1 timing for all of parallel. So that sort of gives you an independent way to just time the parallel command. The commands that are in front of here are also counted in Ceph. They are very quick, but suppose that something else had to be done here and you want to know how long parallel takes, you could just say time parallel. So So just to explain this one more time, the automatic load balancing of GNU Parallel comes from the fact that as soon as there's a core that's not doing anything, it gives that core a new task to do. And so that will be perfect until there are no more tasks to give. So now there's cores that are out of work and there's no more work. So that's where the inefficiency is there. If there was an infinite list of jobs to do, all cores would always be busy and we'd be having 100% efficiency. The imbalance would happen if GNU Parallel did something a little sillier, where it would say, I have 16 cores, I'm going to give them 16 jobs, I'm going to wait until all those 16 jobs are done, and then give the next batch of 16 jobs, right? And that would be a waste, because a lot of those 16 cores would not be doing anything and waiting for the last core to finish. So that would be less efficient. GNU Parallel does it in the most efficient way it can without predicting the future. So it just takes the next job on the list. Now, there might be ways to reshuffle the list that would lead to less inefficiency, but we can't know how long they will run until they've run. So there's really no way to know how to reshuffle the jobs. We don't know which ones are short jobs and which are long jobs. If you ever are in a situation where you do know that, then you would give the long jobs at the beginning and then fill in the gaps at the end with the short jobs. But that, as I said, that only works if you know the duration. Okay, so the time command actually gives you three outputs: a real time, a user time, and a system time. The real time is really the wall time, so how long it really took, and that's the one that matters for that. So I have showed. So there's a question on what this log.txt is. You choose this name. It will be written in the current directory, unless you give it a directory in front of it, obviously. So if I don't specify this, I don't get a log at all. I get no output concerning what was running, how long it took, or anything like that. By making -- job log and then a file name of my choosing, it puts it in the file name. Log.txt might be a little bit undescriptive. You might want a better file name for this, but that's what I chose here. Are there any other questions about the parallel script that I have here? Yes, so the command to visualize the load on each core is htop. But as I explained in the hands-on, you need a second monitor for that, or a second terminal, not a monitor necessarily. But let me just show when it's not using. So here I'm on the teach cluster. If I type htop, you will see on the top here a visual explanation of the load, and there are 16 cores, and most of them aren't doing anything because nobody's doing anything on the system right now. If you wanted to do this for your job, you would need to do that by logging into the node. If you want to do it after the fact, it's kind of too late, except if you're running on Niagara. We do have a website interface called my.scinet, and you can log in after the fact and get a history, but not core by core, it's node by node, of how busy the node was as a function of time, which is very useful. But we don't feed the teach cluster into that at the moment. Okay, so here's a good question. What happens if one of the iterations fails? By default, if an iteration fails, GNU Parallel will take the next job, and so it will not mind that it failed. I think there is an option where you can say that as soon as something fails, it cancels all of them. I forgot what the option was, but if you type man space parallel, it should give you all the options. It will tell you in the log file that it failed. It will have an exit status column, and it will say whatever exit error code it gave. If it's 0, it tends to be, it means that everything was fine. So you can see after the fact if it failed. And then since you have the job log, you can actually run it again, if assuming you fixed whatever was wrong with that particular iteration, and it will only run the ones that failed. So there are some options you have to give to Parallel to make that happen, but it can do that for you. Okay, there's a question about the difference between job log and output. So what output does for SBatch is just take whatever would be printed to the screen by the script if I ran it on the login node. So this time command on the left here would print to the screen. And so rather than having that on the screen, because it's running on a remote compute node, it would now go into this text file. Here, the only thing that is going to output is the output of the awk command, because the parallel command is actually not printing much. Well, I guess the bond break does print some stuff. So everything that bond break would print could go there. The log.txt is extra information. So Parallel would normally not write that out at all. And so that must be a different file. So there's a different file with a log that is just from Parallel, and there's a file for the output of the whole script. And SBatch can send that to a file for you. Okay. Let me go. Right, so that's most of you got some version of this going. There's many ways to fill around with variables and stuff, and I'll talk a little bit about it a few slides on, but that's just the nature of filling with bash shell scripts. So let's look at some common issues that I saw in the submissions. First, a few that they irk me a little bit, and they're not that horrible for this, but some of you just submitted the output of the JavaScript, but not the parallel JavaScript itself. From the output, I can kind of see that you ran it, but I don't know how it was done. So that didn't really tell me what you might be able to do better. I saw one case where people were submitting a screenshot. That is a little bit tricky because I don't know if I'm getting all the information. A text file is much better in most cases when you're talking about code. And I didn't specify this maybe too clearly, but it would have been nice to know the speedups that you guys are seeing. I can rerun it, and this is a fairly reproducible situation where your speedups go from 13, 14 minutes to 1 minute, 22 seconds, 24 seconds. They all kind of are in that range, but it would have been nice if I knew what you had seen. Right, so some of you did, but not everybody. So that's just my gripes. The real issues or things that I could see. The first thing to be aware of when you're doing parallel programming is that there is no magic. There's no magic bullet. There's no, oh, I used this and then it's magic. New Parallel is as magic as it gets, but even it needs a little bit of help. So for instance, if you had your serial JavaScript and you just added n task per node is 16, which means you give it 16 more cores to the script, it doesn't parallelize the script at all. What happens is that the script runs on the first of those 16 cores and the other 15 are idle. So it's actually worse because you're wasting resources. So there's no way that the system can figure out that this is happening, that there are these cores, and then figure out how to modify its own workflow. We have to do that for it. Similarly, new parallel is somewhat magic, but it's not entirely magic. So it's not enough to just put parallel in front of the command and then it is in parallel. I wish it was so simple, but it isn't. We have to give parallel a command and then a set of parameters to fill into the command. And then it knows that it can run those independently and do its job. Okay. Also, and this is just typical for any any coding task, but syntax matters. The computer can't guess what you mean. And so a few things that matter that might not have heard you right away, but might at some other point. Don't confuse nodes and tasks. So nodes are these full computers of 16 cores that we have in the Teach cluster, or 40 cores that we have in Niagara. And on those, you could run more than one task. Those are different. Now, GNU Parallel, what it runs, those are tasks. So if you want to run 16 tasks at the same time, your end task has to be 16. But if you want to make sure those 16 tasks all land on the same node, you have to say, in addition, that the number of nodes you want to run on is 1. So if you didn't do dash node equals 1, chances are, because of the way things are scheduled, that all of your cores were on the same node, but that didn't have to be the same. If this was a very busy system and we had 16 nodes, each with 1 core left, those cores would have been used. And GNU Parallel doesn't like that too much unless you really specify what the different nodes are. So by default, GNU Parallel assumes they're all on the same node, and basically you would not be using all of your cores that you're asked with and tasks for. So make sure you ask for a single node, or if you have multiple nodes, ask for the right multiple of nodes, and then ask for the number of tasks per node. Task per node is typically a bit safer because you don't have to change this if you ever do go for more nodes. So yes, the number of tasks that you can run on a node depends on the cores of the node. Really, the number of tasks that you can run efficiently on a single node depends. If you have 16 cores and you run 32 tasks at the same time on them, it will let you do that. But it really means that the cores are switching back and forth between the different tasks. They can't do them at the same time. They would have to interleave them. And the switching itself takes some time. So that is kind of inefficient. In almost all cases, you want the number of tasks to be the same as the number of cores. Or in other programming paradigms where you're using threads, you want the number of threads to be, the total number of threads to be equal to the number of cores. You don't want to overload the computation. You can a little bit in some systems using clever tricks called hyperthreading. They're not hard to use. They're just a little bit extra oomph. But as a first rule of thumb, number of cores is how many computing tasks you should run. Another thing that I saw and that's a syntactical thing, is that Parallel must be given some input. So you can't just give it a command. You have to give it a command and a range of options, or a range of commands. And so there has to be some way where Parallel reads these in, either with a redirection syntax like lesser than or a pipe. Those are bash specific ways to give input into Parallel, or the triple colon notation that we've been using mostly, which reads the arguments from the command line. There's a 4-colon variation that can read those from a file. So if your parameters are in a file, you can read those from the file rather than having them on the command. It can be useful too sometimes. But if you don't give it any of those, you just give it a command, it will actually wait. It will say, oh, you have the command, and now you want something, an argument to that command, but there is none. So it'll just wait until you type one, and it'll just hang there and until the job is done, and it will not have done anything. Another thing to notice, I saw this a few times, the triple colon is a command line argument as far as Parallel is concerned, which means, because all command line arguments have to be separated by spaces, that there should be a space behind it. If you didn't have a space behind it, it would not have worked. So if you had a case where you thought the syntax was perfect, but it told you that it wasn't working, that might have happened. Finally, and I think a lot of you have realized this, bash syntax is a bit more peculiar than it at first might seem. Like, things that seem intuitive aren't doing exactly what you might expect. And so again, I will spend a little bit of time at least trying to explain what the rules are, and we can go over some examples if you want to see why things are working. It's not that bash is particularly bad, but the syntax doesn't do the same thing as you might be used to if you're, say, writing in Python or C even. It does a a text substitution that you have to know the rules of to make sense of. Okay, so there's no magic. Once you've got the syntax right, though, it will work. There is some extra tricks that you can use that I find useful. The job log is incredibly useful. It doesn't cost you anything, and it keeps track of what was done, how long it took, and you can use it for restart. So should the job run out of time, say you asked for 20 minutes, but you needed 25, the job log will have a record of what was done and what wasn't. And then if you give it, if you run it again with the -- restart option, it will take just the ones that weren't done and redo those. The sef command I found very useful because it's very concise to give you the information about your whole job. There's other ways to get even more detailed information out of Slurm, and that is fine, but this is really nice and to the point. Another nice option could be that you might want an email to say when your job has finished or failed. I tend to do just fail. You'd have to set -- mail type in your bash job script to fail, and then if it fails, you get an email. Now, if you're somebody that submits like hundreds of jobs, that might be too much. You might just want to check yourself at the end. But if you're not running a lot of jobs at the same time, this is a good way to indicate. You could get emails for the beginning of a job, the end of the job, failing, canceling. You can choose those, and you can choose the email too. Though for regular users, we have an email address on hand. So if you don't specify it, this goes to the email that is associated to your account. Another thing that I like to do in job scripts, and in most scripts actually, is to have them abort as soon as there's a failure. So this is a bash command. When you say set, so the regular bash scripts, the way they run is when they run and there's an error, it'll print out that there's an error, but then it will just continue to the next line. And so if the previous part was necessary for the next line to work, that will also fail. But even worse, if the next line is just saying, for instance, echo done, that will be successful. And now the scheduler will think that your job was successful. So making sure that your jobs abort as soon as there's any failure can be a useful thing. How that cooperates with GNU Parallels running of jobs, I am not even entirely sure of. I would have to test this. Let's see. I see there's some questions. I think we looked at that. I'm not quite sure if I understand what the... Okay, so I think the questions are a little bit about how GNU Parallel could cooperate with other parallel running frameworks, either in Python or like PyTorch, like one of those. It depends. If the application already is parallel and efficient, there's no real need to run GNU Parallel on it as well. GNU Parallel is good for serial jobs that haven't been parallelized. If you can run all 16 cores, or maybe there's a GPU, GNU Parallel doesn't know how to run anything on a GPU. So that's not going to help you there. Then just run it. Like just have it use the 16 cores and the GPU and what have you, and just run it with TensorFlow. Sometimes the sweet spot of parallelization in these schemes is not to use the whole node. So imagine that there might be a parallelized application out there. It can use 4 cores. Well, it can use any number of cores. But at 4 cores, it's at its fastest. Then you might want to run 4 of those at the same time with 4 cores. And so that's where you could combine, use a hybrid approach where you have GNU Parallel and whatever parallelization your application already has. But that is really a case-by-case situation. What makes it hard so it's mostly useful for serial jobs or for jobs that you know how many cores they run best on. They all have to have the same number of cores. So GNU Parallel cannot say job job 1 uses 4 cores, and job 2 uses 6 cores, etc. At that point, it would have become a schedule like Slurm, and it does not have that capability. Okay, another thing that I wanted to remark, looking at your submissions, don't trust anybody. Don't even trust my slides in all of cases. But what I mean is, don't just copy and paste things that you find either on the internet, on our slides, if you don't understand what they're doing, or not even a little bit. So I've seen a few cases where people loaded the Intel modules because on one of the slides I had those. They might not have heard here, they wouldn't have, but they might have in other contexts. And so they weren't needed. And if they're not needed, you should really not include those lines. Particularly if you included both Intel and GCC as module load, you would have gotten some sort of warning message saying that you're switching compilers. And so that is, which is again, harmless in this context, but confusing. So load what you need. Be wary of recipes you find online as well. If it says to install a piece of software, especially those, even if it says this is written for Linux, and you say, well, the supercomputers are running on Linux, aren't they? And they are. Those instructions are often written for computers, machines that are just yours, so that you have root access or administrative rights, and you can install whatever you want, wherever you want it. So they'll often say sudo make install, and then you go, I need sudo access, which is asking for complete control over the supercomputer, which you're not going to get. There are almost always very simple ways around that, where you don't have to install things as if you were the administrator. But the recipes you find online are obvious, are often not really specified for that. You're now in the supercomputing club. It's a select club. The majority of people are not running on supercomputers, and for the majority, those instructions work. You are now the minority that runs on supercomputers. You're going to have to learn a few extra things. Okay, so let's talk a little bit about Bash. And I know next week there's going to be a whole Linux shell week, and some of these things will be mentioned. So I'm not going to go into much detail, but these are kind of interesting rules that make Bash differently from a lot of other even interpreted programming languages. The first thing to realize in Bash is that everything is a string. It's just a set of characters. There's nothing else. At some point, Bash will run commands. Those commands will have a name and then arguments. Each of these arguments is a string. They're given to the application as strings. That application might then start interpreting as something differently, but it's just strings, just text. The second thing to know is that spaces in Bash separate command line arguments. So as soon as there's a space, it's the next argument. The only way you can get around that is by quoting. So you can quote them in double quotes or single quotes, and they are very different. Again, that's not like Python, where single quotes and double quotes are the same, or even in C, where one means a character and the other means a string. The behavior inside the double quotes and single quotes is very different, but they exist, especially the double quotes, to be able to enter spaces as an argument. You couldn't enter a space as an argument because a space is a non-argument. It's what goes in between. So that's their purpose, but then they do different things. So one of the different things they do is what happens with variables. So you can assign values to variables, as we saw, and then you can get those values with the $sign. So that's called a variable substitution. So a $sign triggers a variable substitution, but there are exceptions. And the exceptions are there for when you don't want that substitution to happen. And that's called escaping the substitution. So one way to escape it is to put your $sign expression in single quotes. If it's in single quotes, the $sign will not trigger substitution, and whatever it says, it still says. There's an alternative way where you can put a slash in front of a $sign, and that also renders it inactive. It actually gets substituted with just a $sign. And so the slash disappears then, but the $sign remains. That's not true for double quotes. For double quotes, the substitution happens. So if I have a variable, a dollar variable inside double quotes, it will be substituted. If I have it in single quotes, it will not. Now, you have to match them on both sides. That makes sense. But to nest, say, a double quote, to have a literal double quote inside of a quote, you would have to have, again, a slash in front of them. So slash double quote can be put inside here. If I don't do that, if I just do a quote, a double quote, it will end this. It's not really a string, but this string of characters. And the rest now is basically unquoted text. So those are kind of the rules of the game. Another thing that we've seen is that if you have ranges, so the curly braces, one dot dot another value, the range is expanded before variables and not after, and so that's why we had to do this funny echo thing. Then, and this happened to a few people too. This is all true within a single bash shell, but bash is going to call a command at some point, and that command might call another command, etc. Those are called sort of subcommands or child commands. And children don't get all the variables of their parents. So there's two kinds of variables called exported ones and non-exported ones for bash. The non-exported ones are the default, and that means that they're not inherited by a child process. So if I set a variable like the MT variable, for instance, in our script, and then I call GNU Parallel will not get that MT variable unless I explicitly say that it is an exported variable. The way to do that is just to say export and then the name of the variable. It's not very hard. Now, we haven't really needed that because as soon as we invoke our GNU Parallel command, we're still in the same bash script. Bash expands them on the spot. It was never GNU Parallel that expands the variables that start with a dollar. It was always bash at that same level. So it didn't matter that they weren't exported. Bash didn't, GNU Parallel doesn't need them. They're already expanded for them. But it is important if you're doing things like writing a script that is called by GNU Parallel, this bash script, and the bash script uses variables. Those variables have to be exported. Otherwise, the script that is run by GNU Parallel, it doesn't see them. So this is the list of things that you can go through to see what went wrong. Anybody using single quotes with a variable would have seen something funny happening. Somebody trying to do ranges before variables, same thing. So in general, just as a sort of a guideline that I tend to follow, don't use single quotes unless you really want to stop variable expansion. There's a similar mechanism that goes with file name wildcards, follows very similar rules. The same thing kind of applies. So single quotes, you only want if you really mean what is inside here should be taken literally and should not be in any way expanded by bash. Now, GNU Parallel has its own expansion. It has the curly braces. So GNU Parallel will expand curly braces wherever. It doesn't listen to these same rules. It has its own rules. That's why the syntax is different. That's why it's curly braces and not a dollar sign for that. So you can have things in single quotes, bash leaves them alone, but have placeholders for GNU Parallel in there, like the curly braces, that are substituted. So, but in that case, it's GNU Parallel doing the substitution. So single quotes, you should use them as sparingly as possible, only if you really want to stop things from happening. You use double quotes if there's any chance of spaces in an expression. So whenever you use a variable and you're not quite sure if it's going to have a space, and in many cases you don't, you can use double quotes. The double quotes are that's what they're essentially for. Another reason you might use double quotes is if you have special characters. Say you want a greater than character in an expression. Well, that has a meaning in bash, and again, by putting it in double quotes or in single quotes in this case, that they will not be doing their regular job. As I said, these are questions, these are issues of Linux that you can go more into next week if you're going to that course. But this is there's no way around dealing with these at some point. I can write scripts that seem like these are not issues, but they are. I mean, these are the syntax rules, right? That's okay. So, any more questions about this shell business before I go on to the last part and give you some more general tips on what to do in scientific computing? No? Okay. By the way, if anybody has still issues with the attendance test, that let me know. I think it should work now. I think it does, but do speak up if it is not. And if you used your 2 times up before I fixed it, just email us and we'll just add you by hand. That's okay. Okay, so that was the assignment and things that went wrong there. By and large, you guys did a good job, and everybody's put their hands, like try their hand at doing this, so that's good. But this was just one script and one example. When you're doing things at scale, remotely, doing things right becomes important. When things are not working well or are broken, it's harder to fix them if they're remote. It's harder to fix them if they were a job and you had a 200-line script and something went wrong somewhere and you don't know where or when. So there's a few best practices that are always good in scientific computing, but that become very important when you're not just interactively behind your own screen. The first thing to realize when talking about doing scientific computing well and responsibly is that code never dies. There is no such thing as a one-off code or one-off scripts. The examples that I made for this course, I'm sure somebody's going to download them and do something with them, and that should be fine. Even things that you think you're going to use only once, and so you have a little script that parses something and then you're going to save it somewhere, and a month later you're going to go, oh, I had a solution for that and I need something similar, and you're going to use it again, right? If it was worth writing, it's worth running again, and somebody else could possibly use it. So code tends to have a much longer lifetime than you might imagine. And that means that if it's a big mess, it won't get reused, but it won't get reused not because it's not doing something useful, but because people can't either figure out how to use it or whether they should even trust it. Like if you can't sort of look at the code or look at the documentation and go, I know what it's doing and it's going to do a useful thing for me, you wouldn't, right? So now professional software developers deal with this all the time. So they have a bunch of best practices, and not all of them are entirely applicable all the time, perhaps, but computational scientists tend to be not professional software developers. And that means that their focus is very different. Their focus is on getting the results, getting the data processed, or getting the simulation going and producing the publication. The software is just a tool, and that is correct. That is fine, but you still have to keep it, sort of take care of your tool. And the reason that you have to do that is not just because it makes it more shiny. It is because by making something that's more maintainable, better quality, it pays off in the long run. Whenever you have to reuse a bit of code, or say you're a PI and one student finishes, that's great, and the next one comes, you would want that next student to be able to take the code from the first student and understand and run with it, rather than basically to have to rewrite it and waste all that time. So it pays off to have maintainable, reproducible, responsible code in the long run. It's a bit more work initially. And so I'm going to talk a little bit about some common, not too difficult best practices in what I would call scientific computing, but basically any computing that you should consider using. So the first thing is to automate everything. This is especially true or important for scientific computing, because you should be able to exactly say how you got all your results, right? That's anybody ever asked you in your PhD defense, okay, how did you parse this data? You can say, well, I have a script from there for that, and if you want it, I can share it with you. But also for yourself, if the reviewer for your paper comes back and says, oh, I need to do this, you need to do this, but slightly differently. If you haven't automated it, you might have completely forgotten how to do it. So you should write scripts for any computation, any data processing you do, for a record, for being able to rerun it, and to be able to run them in a sort of different way. Right? So everything becomes code. And this is tricky if you're using graphical user interfaces as part of your workflow. And I know some workflows do have that, and they are sometimes an essential part of the application in particular. They're not necessarily inherent in the workflow, but they are inherent in the tool you use. And when that is the case, well, the only thing you can do is painstakingly record exactly what you were doing in the GUI. Keep track of the version of the application that we're using, so you know that the buttons have the same name and are in the same space. And you have to say, okay, click there on the left where the button says login, or and keep a log of every mouse movement, every click and keystroke. This is why GUIs aren't very good for reproducibility, because this is really hard to do well. And you get an upgrade of your application, and now the GUI has changed and it doesn't work anymore. So that's not great. That's why we like scripting. It's very controlled. And since you now have scripts and they're just text files, they're going to change, right? You're going to adapt them or correct them or fix their bugs. So you should use a version control system. Most people these days switch to Git. Git is fine. There's other ones. Don't really care what you use. You should go beyond just renaming your files with sort of a date stamp or a funny description. Version control is there to keep track of managing changes in a set of files. So it keeps historical versions. It knows who did what. It knows when they were changed. Essentially, you have snapshots of all your files at any given moment in time. Now, it works best in text files, because for text files, it could actually tell you which lines have changed. It wouldn't work very well for pictures, where if I changed one pixel, I still couldn't tell, because of the way it's encoded, that just one pixel had changed. The whole version would, the whole code would change. But it's really good for anything text-based. So why would you use it? Rather than, okay, it's nice to have version control, but why? A couple of reasons really stand out. Collaborating on any code is much easier if you use version control, because version control does not just keep track of what changed, but also who did it. Most of them have ways of branching out a code. So you have a code base, you can make a separate branch where you try something out without messing up a working copy, and then you can later join those. It helps to stay yourself organized, keep track of changes. You could see not just, well, if you use it well, every time you commit a change, you give a little note, a little comment that says why or what you changed. And so not only can you see what was changed, but also why. And you can see that months in the past, or until the beginning of the version control project. Another thing that it does, and this is very useful in scientific code, is that it makes your code reproducible in the sense that you will have a code, you created some data from it, or you created some results with it, you published the paper, and you went on and you changed that code to do other things or to be more specialized. And now you have to rerun the same computations. Then you can just go back to that previous version and not even worry whether you properly undid all of your changes. You can run exactly the same calculation again. Similarly, if something goes wrong, say you did make those changes and nothing works anymore, and anybody that does any programming at some point hits this, where they messed up something, they don't know what, but they can't get their code to work for the life. If you don't have version control and you haven't saved anything, you have to start all the way from scratch. You never want to do that. If you have version control, you can go back to the previous version. Yes, your changes are gone, but that version worked, and so you're in much better shape. Okay, so another thing that you should do is comment and document. It sounds optional because it's not necessary for the code to run to have either comments or documentation. It runs, the computer reads it, and so what? The problem with that attitude is that you're assuming that you write code for a computer. And that is only true in a very small sense. The computer reads your code once and then executes it. If it's any useful code, it'll be read by humans. And the computer doesn't need this to be written in Bash or in Python. It could read it in binary, in opcodes, in assembly. The reason we're doing this in a higher level language, and for this purpose, Bash is a higher level language, is because humans have to be able to read it. But not everything that we write in code is very understandable. We don't know why it was written that way. We don't know how to use it. If it's a whole script and it expects arguments, if it doesn't explain what those arguments are, it doesn't matter that it works when the right arguments are given. The right arguments will never be given because the humans don't know how to use it. So it's not optional. You must do this. You must document your code. And documentation and commenting comes in different forms. At the lowest level, in basically the part that is part of the language, sensible variable names, function names, module names, etc., so that you can guess or get a hint from the names of things, what they do. Comments in the code. In Bash, the # starts a comment. There's a school of thought that says that code should not have to be commented because you should write all code such that it is self-documented, documenting and explains itself. I don't subscribe to that at all. I rather have a few comments that are obvious than no comments at all, so that I can't figure out what it's doing. Even if I can't figure out, why do I want to puzzle on a script for like 30 minutes to figure out what it's doing when a few comments would have saved me that half hour? Like that, it's just you know what you did in the code, why you did it, write it down. And then you can go a little further, more in the line of documentation. You can write help commands, so that if I have a command and I type -help, or I type help in the name of a function in say, Python, it actually prints out a useful help command. You can go even further. You might want to write a whole manual if it's something that you expect other people to use, but not read every bit of your code. So especially for applications, you'd want to do that. This is not just you writing documentation and code for yourself, for other people, also for yourself. You will go back to your code 3 months from now, and you will see, and you won't understand the thing. You don't understand why you did it. If you ever looked at scripts or codes that you wrote a few months ago, or even a year ago, and wondered who wrote this thing, and then you realize, okay, this was me, but I still don't understand, you won't remember every detail, right? And sort of along those lines, I don't have a slide of that. Don't write clever code. Clever code gets you in trouble with yourself. You write your clever code, you write your lines of code as simple, as clever and concise as possible. And you go, look, that these neat features that Bash has that nobody else knows that I used to be able to do this command in like 10 characters. But then a month later, you won't understand what you wrote here. And basically, if you want to do something similar, you just have to do the whole thing again. Don't be clever. Clever code means that if you write code as clever as you can, if something's wrong with the code, you are no longer clever enough to figure out what was wrong. So you made the code basically undebuggable. Anyway, that's adding comments can help you with that. And writing manuals for or README files for just general things are a good idea. Another concept that helps in maintaining code is that of modularization. The kind of scripts we've looked at here are so short that you can't really say there's much point in it, but scientific software in general tends to be large, complex, and rather subtle. And so you want to separate the different parts of your software as much as you can. If each section of the code would need the internal details of the other parts of the code, that means that to understand this code, you would have to understand all of it, not just a section. So suppose there's a part of the code that just deals with writing the data out as files in some sort of format. If that somehow intimately depends on how the data is processed or computed or obtained, then if you ever have to change just the output format, you have to understand all of the code, potentially, in any case. So you don't want to do that. You want to make modules for different parts of the code or different parts of your workflow that deal with different functionalities. Another thing that helps with, if you do that, is not just that it's more maintainable in that you can extend it more. You can change one module without having to worry about the other modules. You can debug things. If something goes wrong with writing a file, you can take that part and just write the file and just focus on that. If you don't, all bugs are difficult because they could be anywhere in the code. And codes will eventually show their bugs. What it also allows, if you do modularize, is to test each of those separate modules. If you don't, the only thing you can test is run the whole software stack and just see if it crashes or not. And that's pretty much all you can do. And if it crashes, you don't know where to start. If you have modules, you can make a test just for your I/O writing. You can make a test just for your data processing. You can make a test just for accessing a database. You can make those separate tests, and you should run them every time you change something in the code. And if they fail for the database module, you know that you have to fix the database module. You don't have to look at all of the other parts. So it's an incredibly powerful tool, but it is something that takes some work ahead of time, because when you, especially when people start with a project, you kind of know what you want it to do, and in your mind and even in the way it works, it's step A, step B, step C, and just you have a list of things to do, and it all is interdependent. And so separated that out into modules is not, it's something that takes some practice and some iteration. And the first time around, the way you split things up may not have been the ideal case. And so there's some rewrite. But it does pay off in the longer run. So this one is way more powerful, but therefore also a little bit more expensive. I, for new projects, often do start off just having mostly what was called a monolithic code that does what I want. But as soon as it does something that I want, I try to modularize it and try to split off the parts that that deal with different functionalities. So when you're doing that, when you're splitting things up, you have to think of what those modules should do. And so they should perform a single specific task. They can have several functions in them, but they must be related. So if you have an I/O module, so module does input and output, it might make sense, because they both depend on the format of the file, to have input functions and output functions in the same module. But then it doesn't really matter what was done with the data afterwards, right? So any processing or should not go in there. You want to separate them out in different files. That is useful in combination with the version control as well. It depends on the language that you write in, whether the modules have to be different files or can be. But even if they can be joined in a single file, don't. Just keep them in different files. Sometimes even a single module can be separated in different files. Could be useful, could not be. It depends on the size. But the files happen in the version control, because the version control keeps track of changes file by file. And so it's much easier to find where things have changed in the past if something's wrong with a specific file, rather than anywhere in the code. Make sure you enforce boundaries. So one of the reasons to do modularization is that not every part of the code touches or can influence every other part of the code. So what you want to do sort of is to impose an interface, a way in which the different modules can interface with one another. And that's a little abstract until you see it in action, but that means that if, say, one module had 100 internal variables, you only expose one or two functions that access those variables, and you never see those variables. And so the only way you can change anything is with that interface. So the boundaries between those codes are those interfaces, those functions, and that's how you make sure that the number of interactions between them is limited. The fewer interactions you have between the code, the fewer possible scenarios you have to track down when something is wrong. And so it all comes down to maintainability. Another thing that's really good for modules is that you can write testing routines, and they should all have testing routines. So there's cases where you know it should work. I write out a file, it contains all zeros. So I give an array with all zeros to this function, and it should produce a file with all zeros. That's easy to check. And you say, well, doesn't the code obviously show that it does that? Not until you checked it. And if you've checked it once and there's a change in the code, you might as well check it again. The check is typically fairly lightweight. So simple cases, check that they work. And that way, whenever you make a change, before you either run with that change, you run the tests, and you can really quickly pick up the most obvious mistakes. Of course, you can never test every possible case. You can never test enough to see if your real run will run, because the only way to do that is to run the real run. And then, but you can get more confidence in your code by making sure that simple cases aren't failing, because if they fail, you cannot trust it at all. Talking about failure, checkpointing is another very important technique, and not all applications implement that, but they should. Lots of things can go wrong when your job is running, and so this is even more important for a non-interactive system like a supercomputer. Your job might crash because it tries to use more memory than there is, and so it crashes. It could be because your job is trying to write to your home directory or to your Scratch directory, but you have no more space. You're out of space, you're out of quota, and it crashes. Those are your fault in a sense, but you might not know that, right? Because it's hands off. I need to ask if people can hear me at this point, because someone has lost their audio. Am I? Okay, good. Then it's just one person, which is also sad, but I think we can safely continue. I see only one no, and that's from people that no nodes, but oh. Why am I asking this with voice? If they can't hear me, can everyone hear me? Okay, thanks. I think we're good, except for that one person. I hope they can figure it out. Okay, so let's continue with okay. Yes, so checkpointing. So things can go wrong, like the audio can fail, but sometimes it's due to things you could have known but didn't. Sometimes things go wrong with the system. It's not very common, but it happens that the file system gets sluggish, and you're trying to write out, but it takes too long, and your job runs out of time because it's waiting for the file system. Sometimes there's a power outage. These things happen. So it could be external. And when that happens, if you don't save anything while your job is running, you will have wasted all of that computation time. So in the least thing you want to do is save things as soon as they are produced. But what if the end result isn't there to be saved in any useful way until the whole job is done? Well, you could still try and save as much as possible, such that if, say, the power goes out after an hour into your job, before that hour was done, you saved enough information to be able to restart your computation. And so that's called checkpointing, saving enough information about the state of your system, the state of your computation, to allow the computation to restart if it crashes after that. So to restart at the point when the checkpoint was given. Now, it is theoretically possible to do this automatically, but that would mean that the operating system has to save its entire state, all of its memory, and all of the processes, and save them to disk. And that would take a lot of time. And in itself, not all of that information would be needed. Some of that is just other processes running. So checkpointing, if it's automated, tends to be inefficient, but it isn't. So you will have to do that, or your application will have to be able to do it. And so, some do, some don't. If they don't, ask the developers to put it in. And it's sometimes just called a restart or something like that, but it's the same feature. At regular intervals, it should write out just what it needs so that it could restart from that point. Obviously, it has to have a way to restart then, and that's what you want. And that gets you also out of the problem that some supercomputer centers put limits on how long you can run. We at SciNet like to impose a 24-hour limit. That has a lot of benefits in the throughput section. So when we talk about throughput, our general throughput is really good. But if your job needs more than 24 hours, you really have no other choice but to make sure it can do checkpointing, and so that it runs and maybe checkpoints. And if you're checkpointing anyway, you want to do it frequently enough that it doesn't slow down your job, but gives you intermediate checkpoints for if something goes wrong. So every 2 hours or so seems reasonable. The reason that your application can do so much better is that it will know what to write out. It will know what data is needed, and it won't be all of the data, all of the memory of the system. It will be some subset of variables that it will need. And that's why it's the application's job. Now, GNU Parallel has this feature too. It can use what was done in the job log, see which jobs in the job log are run, which one were successful, and then if you run GNU Parallel again with --resume, it will, I think by default, just run the ones that weren't run yet, but with an extra option, it can also run the ones that failed. And so, since the job log will only have completed jobs, that automatically means that this is a checkpointing. But it's a checkpointing at a higher level, right? Within the subjobs, if a subjob crashes, if that subjob didn't do any checkpointing, that's too bad. The GNU Parallel can't help the subjobs, but it can say have this set of 96 jobs and say in the middle of it, there's 48 were done, the power goes off. You could then go and create a new job that just has --resume additionally, and it would run the other 48 jobs. So that is essentially a checkpointing of sorts. And all it needs for that is to know, because it's at this level, which jobs finished. That's the job log. It's extremely lightweight, but it works just the same. Okay. Finally, we do have to talk about I/O. Writing to files, dealing with files, moving files. Those are all by far the least interesting part of any project. You probably have some sort of research project to do. You want to know how things work. You want to be able to do some sort of artificial intelligence. You want to predict the weather. You want to understand climate change. You want to know how to build a better airplane. You don't want to know how to write a file to a file system. Those are just the results. And as a consequence of this being sort of the uninteresting part, is that you don't think about it. And that is unfortunate because at large scale, the file system, the I/O, the disks, they are the slowest part of the system. They just are. There's a lot of physical movement that goes on. There's a lot of metadata that has to be moved around. This is a computation in a sense and a bottleneck that you will hit. And so not thinking of it all means that you have this wonderful algorithm. It's very optimal, and you're trying to run it, and you're waiting a lot of time either just reading in the data or writing it out. And that very optimized algorithm just takes a few seconds. You're just waiting for the disk. So you don't want that. That means that all that careful effort that you took to create a really nice algorithm is kind of pointless because you're just waiting for the data to come in or to come out. Now, this happens at all scales, even on your desktop or your laptop. The disk is the slowest part, but there's only a few things running on that, and the disk can generally catch up and not have a big issue. It's only at scale that you see this. And what kind of scales? Well, supercomputing scales. So in supercomputers, in shared clusters, there'll be a file system. It's usually some sort of parallel file system that is seen on all of the nodes, and this is very useful. So the files that we had, and we saw it when we were working on the teach cluster, the files that we have on the login node are also present on the compute node. So it sends us, the scheduler sends our jobs to a compute node. We didn't have to transfer the files were there because it's a shared file system. It's also a parallel file system in the sense that different jobs, different nodes can write to the same file system at the same time. And in the backend, there are many spinning disks or SSDs, depending on which system you have, that are all running in parallel. So the bottleneck of running to a single disk isn't there. So you've got no need to transfer your files, and you've got multiple backends. That's great. This is why these are called high-performance file systems. They can do rapid reads and writes for large data sets in parallel from many nodes. Fantastic. The thing is, that comes at some sort of cost. It has to be designed to allow this large-scale streaming, and the pain point is when you don't do large streaming of large files, but when instead you have many small files that have to be separately accessed, may all live in the same directory, and basically it means a lot of work for a shared file system. And you can kind of understand this qualitatively if you think of having Niagara, say, which has 2,000 nodes, and the file system is seen everywhere. That means if I create a file on node 1 of the file system, all of the other 2,000 nodes, when they try and see if that file exists, should see that file now. Now, unless they check, that's fine. They're not notified or anything. But what if they do check? So suppose that all those 2,000 nodes are trying to create a file in the same directory. Well, that's an issue because that directory is basically a list of files, and only one node can add something to that list at the same time. And then all of the other nodes have to constantly be checking if something can be put in the directory. So there's a lot of metadata or communication necessary to make this work. If all those nodes were told there's one big file and you're all running from on your own section of that file at the same time, when you coordinate, that's fine. But these uncoordinated, many arbitrary, random small files lead to poor performance. So you can help the file system, or you can say help the file system help yourself. There's some do's and don'ts that you should not do when you're doing I/O, particularly at scale. Don't write and read small amounts of data to disk. So having one file that is a few megabytes is much better than have 1,000 files that are just a kilobyte. It will read and write better on a shared parallel file system. It is also easier to manage, right? Trying to manage 1,000 files or one file in the directory, if you're doing any sort of cleanup, it's much easier. And chances are these are all very similar files. They have something to do with one another. You can come up with a structure where they can be one file. Many small files also waste space. It's slower to access. Each time you access a file, the file system has to go to see if it actually exists, whether you have permissions to read it, then open it, find which of the many spinning disks it's actually on, and so forth. If you have one big file, all of the things have to be done only once, and then you can just get on with the reading or the writing. So it's sort of different best practices in the formatting. If you have numerical data, so some floating point data, and you write it out to screen, most programming languages would write it out so that you can read it. They wouldn't write it out in binary. They wouldn't give you ones and zeros or strange characters that correspond to those bit patterns. They would write it out in base 10 for you with a decimal point. That is a conversion. That conversion takes time. It's a computation. It's also not lossless because base 10 isn't entirely one-to-one compatible with a finite base 2 representation that the computer uses. So it's slow, it's imprecise, it takes more space. So if you have numerical data and you have lots of it, you should write it in binary. It means you cannot read it, but if there's lots of it, if you have a billion numbers to write, you are not going to read it. So it doesn't matter whether you could read it, you couldn't, because no way you could read a billion files. So write it down in binary. It's faster, it takes less space, it's more precise, it's more scientific. If it's text, you would write it as text. That makes no sense otherwise. But if it's not, write it the way that it's stored in memory. Be aware of the file systems that you have. That's the next point. Some file systems are better at I/O than others, heavy I/O. Niagara has a burst buffer that is better for I/O heavy jobs that do a lot of little files. It's still not great to do that, but if you have to do that because of your workflow or because of an inherited application that you must use, there might be better file systems than the general home scratch and project. Other systems, the general purpose clusters in Compute Canada, have node local storage. That gets rid of the shared part of your project, so that you can write a lot of files there without hurting the general performance. And then finally, if your files fit in memory and they're temporary files, say your workflow creates lots of temporary files, but they're not that big and they would fit in memory, you can use what's called a RAM disk. It acts like a storage device, but it is in RAM. And RAM is really quick. It is not shared. It doesn't care about there's no physical moving of a read head or something like that. So that's the place you should put things. So you have to figure out when you have I/O heavy stuff, where you're going to store your stuff. You might not. I didn't put this option here, but maybe you don't need those temporary files. Maybe there's a flag that says, don't write the temporary files. They just slow me down. Use that option or write them less frequently. Write them as one big file instead of 1,000 little files. Those options might exist. Okay. And the reason that it's important to do these things in a shared file system is that if you can lower the load on the file system, since it's shared, if the load is high, all of the users feel that load. So if somebody's really doing bad I/O from many nodes on the cluster, all of the file system becomes slow. And so that's the only part that is really completely shared. And so that's the only part where it really matters whether you are sort of using it responsibly. If you have inefficient jobs from a CPU point of view, we don't like it because we know what you could do more with your resources, but you're not directly hurting other people. With the file system, that's different. Okay, so that's pretty much all I had. Thanks all for being here. If you haven't done the attendance code yet, the attendance code was 1. Take the test. I hope you've learned something, or that we've at least showed you what supercomputing is about. This is just the first week of a whole summer of HPC training. I know a lot of you have signed up for some of the other ones. If you haven't, most of them are full, but the recordings, like for this course, will be posted. So at least you can view them. Don't forget to take the attendance test. If you haven't done your assignment yet, but you got some ideas by what I said today, and you want to try it out and then still submit it, you can. The forum will still be open, and we'll keep it open indefinitely, although at some point we will probably pay less attention to it. But for the coming few weeks, feel free to ask questions there. We'll also, in the near future, send you an evaluation survey, particularly because this is a new format that we haven't used before. Please fill it out. Let us know. Your feedback will be much appreciated. Okay, that was the end of the course. Thank you all, and I hope to see you in the next courses as well.